Thank you, everyone, for joining us today. It's really great to be here. Thanks to the team for the invitation, Alex, Konrad, Paula, and all the rest of the team. It's really great to be here in Munich, opening this session today. I was actually watching the news this morning and was flattered to hear that they were saying it's going to be the hottest day in the year. I say Neo4j is in town, but it was about the weather, of course. Anyway. But it's great. It's going to be I think they've managed to get an amazing lineup of presenters, so it's only going to go uphill from my presentation here. So I'll spend these next 30 minutes talking about graphs, of course. I know there's loads of experts in the room, but there's also people that are relatively new to it. So I thought, let's try to level set a little bit and introduce the concept of graphs. I will do it in the context of AI, of course. And because I believe that graphs can be really your big advantage in the sense that they will multiply the value of your data. That might sound a little bit like a marketing-ish slogan, but I'll explain what I mean by that, because I think there's this genuine value in it, and I think it's very timely, because now is the time to make your data AI ready. I'm sure you've heard the expression from the likes of Gartner and others. And we don't control the speed and at which LLMs are evolving, right? That's only going to keep accelerating in a way. They're going to get better. They're going to get more efficient. But what we do control is the state of our data. And that's what I mean by getting your data AI ready. So we have to make sure it's our responsibility to get the most value out of it, right? At least all the value that this data holds. And normally when you're in the data space, it's common to take kind of a cautious or like a conservative approach and say, maybe, take it easy, slow down and wait till these models get more stable, more reliable. You're not gonna get anything like that from me today. I think it's the opposite. I mean, I think it's time to accelerate. I mean, we of course will put guardrails around this technology. We'll make sure that we ground the LLMs with trusted sources of data. But we will do all that in the same way we use the brakes in our car. I mean, it's not to slow us down. It's to help us going faster, but doing it safely. So that's my kind of my thinking around this situation. And I'm also convinced that the future of AI is going to be the result of the convergence of the two main types of artificial intelligence out there. Of course, there's the most popular these days, represented by large language models and generative AI, which is the more, if you want, more opaque, more implicit. That's the sub-symbolic AI, represented by neural-based systems. But then there's the other type of AI, which is the more transparent and more explainable, represented by knowledge representation systems like knowledge graphs. So if I manage to convince you of this, and we agree by the end of my presentation, well, I hope you'll get out of this session with the conviction that you need to have both fronts covered, right? The two types of AI in order for your AI strategies to be successful. So that's my plan. We have a lot to cover, so let's get started. And I'll start with a bit of an intro. So I've spent the last few years working with organizations like yours, helping them adopting graph technologies. And one of the things that I've observed is that I was talking about getting all the value of your data, but I see organizations ignoring a good part of the value in their data by ignoring a critical aspect in it. And that critical aspect is the relationships. Right? The relationships as in the connections between the data points. So this is the connections between the references between the records in your data warehouses, the references between the documents in your document databases. So these relationships capture the context and to some extent the semantics of your data. And at Neo4j, we believe that these are as valuable, if not more, than the data points themselves. And we believe that because you get three things out of these connections, these relationships in your data. The first thing that you get is connections, relationships, build bridges across data silos. So you get connected data. The second one is they're going to enhance, they're going to make a lot better the process of retrieving information, and retrieval is the R in RAG these days. I'm sure you've all heard about RAG, unless you've been living under a rock. It's the way that AI systems get data and use data from your enterprise systems. So we're going to see, and hold it thought, because I'm going to talk a lot more about that. We're going to see how graphs augment and improve this process of retrieving information from your enterprise data. And finally, the third thing that you get from relationships is that when analyzed at scale, they reveal patterns in your data that are extremely important to your business. And these patterns are nothing but shapes in your data, right? And I'm going to give you some examples. Because a shape can be a ring, right? A ring as in a loop in your data. So a link can be representing a case of fraud in scientific research, right? So this kind of situation where there's cyclic citations in articles, right? That can be done by teams or individuals that want to artificially augment their impact metrics, right? Or they want to create some form of perception of consensus around certain topics to get benefits in a fraudulent way. So that's a ring. And think of trying to identify a ring if your data is represented in a flattened way like the one that Alex showed a minute ago. It's not an easy one. But if your data is represented as a graph, it's going to be more natural. We'll see that in a moment. Another shape can be a star, kind of an hourglass, kind of a shape where things converge into a critical point. And that can be representing something like a critical manufacturer that's producing a component that's critical for some drugs or for some elements, and you have a number of things depending on it. If something goes wrong there, some kind of contamination, some kind of geopolitical situation, that can have a massive impact. So you want to identify these kind of dependencies on critical points. And that's another shape. It can look like a star, it can look like an hourglass shape. And another one that's hard to identify if your data is in the form of tables. I'm not saying it's impossible. We do that, and we have to load that into memory. You have to kind of rebuild the graph. It will be a lot of lines of Python, but there's more natural way to do that, and that's what we're going to see here. So essentially, none of the existing systems in your existing architecture is going to help you uncovering these shapes in your data and translating them into value. So a fundamentally new approach is needed, and I'm here to introduce your data's new best friend, which is, of course, graph. And graph is simple and intuitive, but at the same time, it's really, really powerful and expressive. So what you see there is a very simple data set with all the elements in the graph model. So in the graph model, you have two main building blocks. There's, that's pretty cool. There you go. So there's nodes, the circles, that represents things, entities, like people, objects, locations, events. And then there's relationships that connect them, right? That connect them to one another. And both nodes and relationships can be enriched, can be characterized with properties. You see how a node has a collection of properties there that represents a person, and we have the name, the date of birth, the employee ID. So what you see there is it doesn't really need an explanation, right? So you see that there's an individual that works for a company. It's a particular employee, is the CEO, and the company is headquartered in a city. I think that this doesn't really need explanation because that's the way we think about any particular domain, right? If you get together with your team to discuss any subject, or even if you go into data modeling, you probably will go to a whiteboard and represent, which are the critical elements, how they relate to each other. So it's kind of a natural way of representing things. Now, I'm sure some of you in the room might be saying he's called that a data set. That looks more like a visual representation of the data, and you would be right in both cases, because this is what we're doing at Neo4j is we're sort of inverting the paradigm. So for a very long time, we've been storing data the way you saw it in Alex's slide, so in tables, and then putting a lot of effort in presenting it like that, so that our business can make sense of it, can understand it, and do reasoning on it. Now, I was saying that at Neo4j we're inverting that because this model is the one that we use to store, to persist, to query, and to analyze the data. So that's exactly what the shape of the data as we store it. And when you store data like that, when you model data like that, and you pair it with a pattern-based structured query language, Cypher, then which looks something like that. Then surfacing the type of patterns, the type of shapes that I was talking about becomes trivial. And I'm giving you an example here. I don't expect you to be experts in Cypher, but I hope it's understandable. So I'm using the same color coding. So the red nodes are individuals and the blue nodes are companies. And what I'm showing there is the logic that probably LinkedIn or any other professional network would use to send you a recommendation in terms of who you should be following, which companies you should be interested in. And what it's doing is the exploration starts at a node that represents you down here, and it navigates your working history, which companies you've worked for over time, and then which individuals you've worked with, which are your ex-colleagues from the past. And then we can keep navigating and find which companies do they work for. And there will be patterns, right? And you see that there's 2 or 3 that are converging into a given company, right? So you see that there, this blue node represents a company where 3 of your ex-colleagues, sorry about my pointing here, 3 of your ex-colleagues are working for at the moment. So that's I understand it's not rocket science, but it's an interesting pattern, and it might be interesting for you to know that, hey, 3 of your ex-colleagues are now working for Snowflake, right? You might want to follow this company or connect with them. And that's achieved in a very concise fashion with a pattern that's saying, well, start navigating from an employee, that's you, and navigate the works at relationship up to 3 levels. I've decided to cut it after 3 steps away, and then just aggregate, and the number of common paths that take you to that company is the strength of the recommendation. So it's a pretty simple expression to capture a reasonably sophisticated logic, right? So that's what I mean by having data represented as a graph and having a language, a structured language that leverage these structural patterns, structural features in your data. Good. So I've talked mostly about the expressivity of graphs, but it's worth spending a couple of minutes on the platform behind this model. The platform is Neo4j. And I want to talk about 3 performance or 3 characteristics of this platform. The first one is the flexibility. In Neo4j, we don't need to define up front the structure of your data. You can establish some constraints, but you don't need, like in the case of relational databases, a perfectly clear and rigid definition of the structure of your tables and the data types. If you think of relational databases, once you've defined a table, you can only insert rows that align exactly with this structure, right? In terms of data types, in terms of required fields. And if you want to make that evolve over time, you have to go through migrations, which are not the nicest thing. I mean, if you've been in that space, you know how data migrations in the relational world are not the most nice thing to go through, and they don't particularly add flexibility to the process, especially in the early development phases. It's important to be able to have your model evolve over time and grow organically as you keep adding sources or as you keep changing it, right? So this flexibility is native in Neo4j in the sense that as long as you describe data in terms of nodes and relationships, you're good. You don't need to kind of formally or rigidly define what that shape of your data is. Another conversation would be, is it useful to do that in some cases? And we'll see that it will be, and it's good to sometimes overlay some form of semantic description of your data. But you have this flexibility, which accelerates and introduces this agility in the development phase. The second one is the performance. I was saying that when we invert the paradigm and we store the data as a graph, what we're doing is we don't have tables. We don't persist data in tables. What we have is kind of a let's call it kind of a navigational storage, where we have the pointers, the connections between nodes. They are persisted in disk and then mapped to memory. And what happens is, if we compare it to the way relationships are managed in the relational world, where they actually are not. I mean, it's like through foreign keys, right? If you have a connection between a customer and a product, what you will have in a table is a reference that matches another value in another table, and you would have to scan these tables, these indexes, and find a match, and then determine this customer purchases this product. So you have to work these relationships out at query time. In Graph, you don't have to, because these connections are persisted. So what you're doing effectively when you're navigating the graph is you're chasing pointers, which is a lot more efficient. And that's where you get the performance improvement, the speed in deep traversals. So that's the second characteristic that I think is worth mentioning. And then the third one is the predictive nature of graphs. So typically, when we build a predictive model, we will look at features of individuals. I mean, I like to quote here a book by Professor James Fowler that's called Connected, and he takes a couple of examples that are quite interesting, and he tries to predict whether an individual is going to vote in the US or whether they're going to suffer from obesity, and he tries to build up a predictive model. And it's interesting that he built a much more robust and better prediction if the focus is not only on the individual's features, but in their neighborhood, and the neighborhood as in the family, friends, colleagues. And even more mind-blowing is the fact that if you extend that network to friends of friends, the prediction becomes even better. So again, having a graph representation and being able to extract these structural features easily and then inject them on your machine learning pipelines is another great advantage of graphs. So this is the third characteristic. We like to think of it as what's important, what's unusual, what's next in the graph. But the idea is that we can leverage these structural features and make use of them in a really efficient way. Then the second part is, we've talked about these performance characteristics of the platform, but there's also the idea of capturing semantics, capturing the meaning. And there's two main approaches to it. And I kind of hinted at it in the opening. So there's the what I call more opaque or less explicit, which is the sub-symbolic approach, which is the one represented by neural systems. And the way we capture meaning in this space is by using this vector representation, this idea of embedding. Right? You might probably be familiar with this. So an embedding is kind of a numeric representation that captures somehow the essence of something. It can be a word, it can be a paragraph, it can be a video, it can be an audio, it can be anything. And you can pass that whatever to a model, and it will give you a vector that captures, like I say, somehow magically the essence of it. And what's interesting about this representation is that it acts as a proxy of semantic similarity. And what that means is that if two things are topologically close to each other, because these are vectors and you can compute the distance between them, so if two things are close to each other, it means that their meaning is related, is close to each other. So that's the interest of these kind of representations. But then there's the other, more symbolic, more explicit, more transparent, which captures the same. Here, what we're trying to do is, okay, I want to capture the notion that an apple and an orange are both types of fruits. So in a graph, I would put something like that. I would say, well, these are two entities or two categories, and they are subcategories, and we can put it in a hierarchical representation of the notion of fruit. That's great. That's something that I can understand. And the right-hand side, yes, it's kind of built into that vector, and it happens to work, but I don't really get it. I mean, it's not for human consumption, let's put it like that. Now, when we have these two representations, we can now do comparison. Like I was saying, if we compare two vectors, and there's two main ways of comparing them, to Euclidean distance or angular distance, proximity in the vector space means semantic similarity. That's great. That just works. It's amazing. I mean, we just have to trust the model that builds these vectors, but that just works. Hard to explain, but it works. Now, on the left-hand side, you see the equivalent of similarity computation, but then on the graph space. And we have a collection of algorithms that do that for you. It can be done based on the fact that two nodes have a strong common neighborhood. That's based on Jacquard and overlap similarity. If you data is structured in some form of taxonomy or hierarchy. There's taxonomy-based similarity metrics. You can see some of them here. But the important thing on this side is that you can always explain that, and it will be something like this here. You can say, okay, the apple is similar to the orange because they have a common ancestor, which is the notion of fruit. So that's very explainable, and that's important, because we're going to see how the explainability is key, especially in the interaction with LLMs. And then finally, with these two ways of comparing comes to two ways of exploring the data and searching, doing search. Search in the vector space is basically you define a point, your question, your search term is going to define a vector, and you will find anything in proximity of it. So it defines kind of a circle, a space, a multidimensional kind of sphere, and anything that falls in that space would be semantically similar. In the graph, this search would be based on the graph exploration, graph traversals. Now, the great thing is that these two approaches are very different, but are very complementary. And it's great that both are supported in Neo4j. That's not news, because that's been around for a few, it's going to be a couple of years now. And what's great is that in a graph, you can store vectors. So we can have, the model doesn't change, so you see it here. Now, the thing is that you can add as properties of a node something that's a vector representation, and that can be indexed. And that's great, because now we can combine the power of vector search and vector similarity with that of the symbolic representation in the graph. And we're going to see what that means in a moment when we come to the retrieval in AI applications. So both types of representations are present and available in Neo4j. You have the link to the document there. Good. So this is not a vision, this is a reality. So I know it sounds amazing, but it's something that leaders in all industries are already embracing, and 75% of the Fortune 100 are already using graphs, and that includes, as you can see, top retailers, top pharma companies, some of which are represented here today, automakers, banks, and the list goes on, telcos, etc. But I don't know how I'm doing for time, because I don't have the timer here. How much? 10 more minutes? Good. So let's speed up. So let me skip these two. I thought they were meant to be hidden. Give me just 1 second, because I want to jump into the AI side of the presentation. So I said that my thinking is that the future of AI is going to be the convergence of these two approaches. And I'm going to try to explain why I believe that agents, or Gen AI in general, do need graphs. And I'm sure you've all seen this kind of contradiction in a way. So there's a huge promise on the value that this new technology is going to deliver, and this is just a random report from Bloomberg, where it's kind of quantified in over $1 trillion in revenue in the next few years. But at the same time, we keep hearing that organizations are struggling to go past this prototyping phase and getting projects into production and getting actual value from these deployments. So why is that? And there's a number of reasons, but the key one is that sometimes there's a bit of misunderstanding about this new technology and the fact that it's non-deterministic. It's hard to explain. It creates some skepticism from leaders, because it's hard to build systems that rely on something that cannot be explained, or on something that can behave in different ways in reaction to the same question. So that's the key, I would say, obstacle to the adoption. And the reason, like I was saying before, is that we have no idea of what happens inside these kind of big models. We might get the impression that they can explain themselves, but it's important to understand that, as you say, you can. I'm sure you all have interacted with ChatGPT, ask a question, and then ask it to explain how it came up with this answer, and it will produce an explanation. But it's important to understand that this explanation is itself generated as well. So it's by no means a description of what happens internally to produce the answer. So explainability, attribution, so being able to, these systems know lots of things, but they can't tell where they learned them from, right? So all these things create problems, especially in highly regulated industries where it's not sufficient to provide answers, but you have to explain where do you get the information from. And this is a test. I know we're past the time where we used to do these type of jokes, but it's kind of, it's a test that I run every time there's a new release. And this is on for something, it's a couple of weeks ago. But it's just an example of this idea of kind of a hallucination, but it's also the autoregressive nature of these systems, in the sense that when they get something wrong, the answer is kind of used to continue the conversation, and it gets even worse and worse. And an example of that is, well, I ask a simple question like, give me European capitals that are south of Rome, and it's very articulate, and it tells me being south of a place is having a lower latitude, which is perfect, and it gives me a list. I happen to be from Madrid, so I said, well, I'm missing Madrid from that list. And I say, well, and Madrid, of course, is not there. And I say, of course, you're correct. It's not there because it's not south of Rome. And it gives me the latitude, And basically it's telling me that 40 is bigger than 41. And it's getting it obviously wrong, but it's trying to explain, it feels like it's south because it's very hot there and blah, blah, blah. So it tries to convince you, and I understand what being north of south or south is. But if it's an area where I'm not an expert, I would struggle to determine if what I'm getting is real or not. So this is a characteristic that we need to understand, and that's where the idea of grounding system comes from. So we have to make sure that we can provide domain-specific, our enterprise knowledge to these models so that they can provide answers that are not necessarily generated, but grounded based on information that we trust and that we have control over. So that's the idea of grounding. And the answer, like I said before, and I'm sure you've heard about it, is RAG, at least the one where we are kind of, as an industry, converging. And we believe that graph can augment this approach in what we call graph RAG. And just a refresher for those of you that are less familiar with this idea of RAG, but it's pretty simple. And graph is basically RAG, where the retrieval path includes a knowledge graph. But the idea is pretty simple, right? Instead of having an application up here, where am I pointing? Oh, here we go. So here we have an application to which we can ask questions. Instead of having that application just talking to an LLM and producing answers, what we're going to do is have an additional step where this application is going to go retrieve some information from trusted sources. It's kind of a generalization of the approach that we take when we upload a PDF to ChatGPT, and then we ask questions about this PDF. I don't want ChatGPT to give me random answers from the training data. I want it to generate answers based on this PDF. Now, if you think of these at enterprise scale, there's loads of PDFs, there's loads of data sources. So I don't know up front which is the one that's going to be relevant. How many minutes? 1 minute. Oh my gosh. Oh my, apologies. I need a timer here. That's anyway. So basically, the approach is given a question, I need to find which are the relevant sources, retrieve them on the fly, basically, and that's what the retrieval step is for, and then build them in the answer so that whatever the LLM produces is grounded on that information. So very quickly, because and this is what this would look like, and without going into too much detail, these days, one of the standard ways in which we offer access to sources of data is through this MCP protocol. And when you build that into something like now, instead of ChatGPT, I'm using Claude. So I ask the same question that I was asking before, and now Claude knows that he has access to a source. I'm saying it has access to a source that can answer that question, and this source is, in this case, Neo4j. So what it does, it will translate that question into a Cypher query and retrieve an exhaustive list of capitals that would match these answers. So in this case, it's grounded in information that I have control over. Now, that's the French version of it, because I presented these a couple of weeks ago. But anyway, the idea is we can still leverage the linguistic abilities of these systems, but we still ground it with a trusted database. Now, I was talking about how graphs multiply the value of your data. So the way they do it, and I'm going to go fast over that, is by giving you a rich collection of retrieval strategies. So ultimately, these applications, these AI applications, are going to need to retrieve data from your enterprise systems. Now, if we offer a rich collection of strategies, we're going to be able to get the data in so many different ways. And I've shown briefly in the example before the possibility of generating structured queries. In this case, it was Cypher. But we can combine search based on the vector index that I talked about before. We can contextualize that with navigation of the graph. We can do exclusively vector search as well. We can define fixed patterns. I mean, the idea is that we can offer a rich catalog of strategies that will make sure that we get all the value of your data, that these systems can get all the value of your data. Well, I'm conscious of time, so I really don't want to go too much over. But the benefits of taking this approach is that we get three things. You get a much better accuracy. It's easier to develop, because we saw that as a developer, as a data person, it's much easier to deal with the symbolic representation. I can understand a graph, whereas it's harder to understand a vector representation. And then we have the explainability element. So we can bring this additional important element, which is explainability. I'm going to stop here because I think I had some additional elements, but I'll share the slide with you and I'll hand it over. Apologies for that. But thank you very much. I hope that was a bit of an introduction, and thank you.